Hello, everyone. My name is Mads Barami from Wolfram Research. Welcome to the fifth session of live coding series with Andreas Lauschke. For those of you who are joining us for the first time, let me say that Andreas has a master's degree in financial mathematics from the Technical University of Berlin, and he has been using Wolfram technology for more than 25 years. During his live coding sessions, Andreas will live code the key features of Wolfram language that are useful in particular in data science. You can find the recorded videos of his previous lectures on Wolfram YouTube channel. I should add that Andreas has also uploaded his notebooks together with some homeworks on Wolfram Community, so you can directly, reach out to Andreas. Today's live coding session is entitled as Dataset Query and Web-Based Data Scraping. Without further ado, let us welcome our instructor, Andreas Lauschke.
Yes, hello everybody. Good evening. Today is my fifth session and I will be talking mostly about the dataset and the query, and then later talk about web scraping of free data on the web. The dataset I will bring to a close today. We've had it for 4 sessions, and I will also introduce the query. The query is the underlying query framework for the dataset. And it is so incredibly powerful that you will want to get familiar with it so that you can use it on your raw data. The query does not have to be used together with the dataset. It is incredibly powerful and can be used on raw data, which is really an extension of the features we've had in the past, because the query also understands right composition, left composition. Although it's not called left composition, it's just called composition, but keep in mind composition means left composition. And of course we can use it with prefix, postfix, all these good ways of creating compound functions and operator notation and so forth. So it's incredibly powerful and flexible and allows you to make very advanced queries on your raw data as well. And then I will talk about the free data that you can find on the web. We can use the traditional import, very traditional methods. We can use XML processing. The Mathematica system has very advanced XML processing since version 4.2 in 2002. We can convert HTML to XML. And we have a new framework for web execution with the web execute function since version 12. And in the next session, I will talk about outlier detection methods, some math about it, and the new outlier detection function in Mathematica 12. So for today, most of the examples of today will follow a particular 3-element pattern. I will show a list of 3 elements. One is a data set of a particular query. And then in 2, you will see the same display, the same output, but done with the corresponding query of the query that we've used in step 1 applied to the data set. And in the 3rd one, we will use the very same query, I've underlined them here, on raw data. And I intentionally do it this way because I want you to see that 1 and 2 produce the same output, and that 2 and 3 use the same query, right? You see query of, and then in blue some query. So I want you to see how the query is constructed. It is the same as applied directly to the dataset, and then the same query on your raw data, to underscore this point. You will find that 1 and 2 look identical in terms of output, and 2 and 3 use the very same query construction, query of some query. And we'll follow all syntax examples of the details section in the help browser page for dataset, listed under part operations, dataset queries, common forms, and more specialized forms. So our program for today is that we will go through all of these cases that we have listed here in the help browser. Right, every row here, because I want to show you this with all these 3 elements that I've just shown you further up here. So each and every one of these rows I will show and I will explain. This is our main program for today. And in order to have data with moderate complexity and difficulty, I'll use again the planets data. The planets data is absolutely ideal for this because it's not too easy and not too complicated. You will remember that the planets data contains a third column which is an association of the moons, and that makes it hierarchical data, not tabular data. And there is some data missing, right? Because some planets don't have moons and some planets have moons for which we don't know mass or radius, right? So this is what I would call moderate complexity, and I think this makes it ideal for what I would like to show today. And I have copy pasted every one of these dataset rows. So you will, in every example, you will see the row copied from the web browser, and then I will show you the particular examples that I've picked in order to explain the point. So let's get started. The following part operations are commonly used to extract rows from tabular datasets, right? I've taken this directly from the web browser. So if we use the bracket notation and then we use the named row, then we're extracting that named row. I mean, we assume we have a data set that is of appropriate dimensions and has the proper formatting, right? We need the rows, we need the columns. So I'm saying if applicable here because it goes without saying that we need a properly formatted data set to begin with. So as we do this, all right, let's load it. And as we do this, I'm now extracting just Mars, right? Mars is one row in this data set. And what I'm getting now is the properties for Mars. The first column is mass, the second is radius, the third one is the association of moons. And in the case of Mars, we have two, Phobos and Deimos. Next, please note that the first and second element are identical. And here all I've done is that I'm performing the same query, right? What I have here in bracket, double bracket notation, I have as a simple function application here and then at PL, right? PL is this dataset. So we're also applying it to a dataset here, but we are specifically taking the query as its own element and then use that very same here query of Mars in quotes on the raw data. All right, and here we get an association. We do not get a data set because the PL raw is just the normal of the dataset data, which means it's an association, right? So this is the format of all the lines that we have up here, and we'll go through all of these examples. So note that here these are the same queries, one in column 2 applied on the dataset and the third one applied on the raw data. Okay, so we don't just want to extract one row. How about we extract multiple rows? So how about we do it with Earth and Mars? Earth and Mars. So now we get both here, right? We get Earth and Mars, and here now we have the moon data in the associations displayed as a third column, right? So we have the moons for Earth and for Mars. For Earth, the moon is called Moon, and for Mars, Phobos and Deimos. Again, identical output in the second column. And here we get the same query that we applied for the second output in order to get the association from the raw data. Okay, so we don't have to name them with the named row. We can also use indices. So this would extract the first row. And here we have the first one that would be Mercury. And Mercury doesn't have any moons. So we get the empty association here in the output. Right? No moons for Mercury. All right, we can also extract the nth row. So let's pick the fourth one, and that's Mars again. So we get the same data that we had before, right? There's 6.41 times 10 to the 23rd, 6.41 times 10 to the 23rd. So, as we all know, the fourth planet is Mars. Okay, so just as we know with the part syntax, -1 means it's the last element. So in this notation, we're getting the data for the last planet. So again, identical output in the first two and identical queries for second and third. And here we get the raw data as an association. Okay, now obviously we must be able to extract rows m through n, and this is again the typical part notation that we know, right? We say then 2 semicolon semicolon 4, and we get this output. We also must be able to extract a set of numbered rows, so now we just put them in a list. Same as we know from the part notation that we've been using for decades. So here's the first table. I'm now picking rows 1, 3, 5, 6, and 8, right? So that's Mercury, Earth, Jupiter, Saturn, and Neptune. Those two, and the version using the association. Note that 3 of them are clipped out here. Okay, the following part operations are commonly used to extract columns from tabular datasets. And this is very similar to how we are constructing tables in the kernel, in that we simply put all as the first element of it, right? Because it progresses in a table in the kernel, it progresses. First one is row, second one is column. So if we want to look at the columns, we have to make the column query across all the rows. If we don't, then, well, we don't get the full column. So we have to go through all the rows, and that means in the second level here then comes the column specification or query or function application. So here we do the same thing now, but column-wise, not row-wise. And the first column is mass, and here I'm showing the masses for the planets, right? All I needed to do was put on in front of it. Okay. So we also have to be able to extract a set of named columns. So now the following examples are similar to the first ones, because if we want to be able to extract a set of named rows, we also have to be able to extract a set of named columns. So here I'm now going to the rows and query across all the rows for mass and radius. Those are columns 1 and 2. And the association form. Okay, obviously then also the first column, right? This is now very similar to the row version. So here it's the first column, and that was mass. The nth column, so let's pick the second, that was radius. Here are the radii. Extract the last column, okay? Well, that is going to be the association of moons. And here you see them, right? This is now the last one. And that's a fairly long association now. We can scroll through it. I'll delete it, but it also makes the point again that look how concise and succinct the dataset is, right? Because I now can interactively click into it. For example, for Saturn here, we have 61 total. So we have 61 moons that we are aware of. So I can use this interactively and click through it, and here 1 through 20, so I can also now scroll through those screens, right? Makes it much more easy to interactively deal with the data rather than getting this big monstrosity here, which is so big for this that I will simply delete it. Okay, so the last column, wait, I just had this. I think I made a mistake. I think I put the same line twice here. All right, so in the next one, we want to, I deleted the output, of course. Okay, so in the next one, we want to extract columns m through n, and here we need columns 2 through 3, and 2 and 3 are radius and moon. And radius is always a number, it's a quantity here. And the moons are, well, associations. And here we see them. right? Again, ordered by row, but then per row we have these columns. Radius and moons are the columns. For Mercury, empty. Venus, empty. For Earth, we find 1. Mars, we find 2. And then when it's getting too many, then we have to click through it interactively. So again, 61 for Saturn, just click on it and we get the data here. Okay, incredibly powerful. And again, the long output. More concise if we pick 1 and 2 and not the moons. So here we say 1 and 2. This gives us a much more concise output. And here we see again, mass was column 1 and radius was column 2. Okay, extract a subset of the columns. So now I want to specifically pick them with the list, these braces, and we get this output, right? It should be the same. 1 through 2 should be the same as 1 and 2. All right. Okay. Like part, row and column operations can be combined, right? It would be pretty bad if we couldn't specify a cell with row and column specifications. So if we use the row and column indices and bracket notation, then we're taking the cell at the nth and mth column. No, not evaluate there, evaluate there. Sorry. Okay, so if you look at 3 and 2, that would be the third planet, that would be Earth, and the second column is radius, so here we find Earth's radius. And you're reminded, if you have a data set where we just return one expression, right, one number or one quantity, and we don't get the data set, but we're getting it returned as if it were just a query on the raw data. So extract the value of the named column in the nth row. Okay, so here we're using an index for the row, but we're using the named column for the column. So here we get the same result, except I'm saying I want the radius, which happens to be the same, the second column, but here I'm saying specifically I want the radius. What if I don't know the column name? What if I don't know the row name, right? So here we take the cell at the named row and column. So here I say, give me Earth's radius. Again, the same output, right? It's 3 times the same output, but what if I don't know row or column name? Then I couldn't use these forms, but I have to go by the labels of the rows and the columns. Okay, the following operations can be used to remove the labels from rows and columns, effectively turning associations into lists. So let's just look at bracket values, and here we see that we don't have the rows there, the row labels. That means we don't know which planet it is, right? I don't think this is a particularly useful application here, but oftentimes we just want to have the column representation, not the row representation. Okay, so we can also remove labels from columns. So let's apply that here. So again, we use all in the first, and we bump our queries one level down, right? So now we use the values here in the second element, not the first one. And now you see that we have row labels, but we don't have column labels. Again, perhaps not the most useful application, but oftentimes you are interested just in the raw data when you do your mathematical applications. Here you can turn off the column labels and the row labels. All right, we remove labels from rows and columns. It's the logical next step, then we do it for both. So we ask for values, comma values, and now we don't have row labels or column labels. We just have the raw data, but in a data set, right? This is a data set without displaying the row and column labels, but still as a data set. Okay, so next, let's do some function application. So here are some common forms of query that use function application. In this case, we apply f to the entire table. right? We don't specify rows or columns. We just say dataset and then apply this particular function. So let's round all the numbers because not all of them were integers. So here just say PL round, query of round applied to PL, and so forth. Query of round applied to PL raw. So these are now all rounded to integer. And to show you this, let's look at PL raw again. PL raw. Let's look at the radius for Mercury. It's 24397 kilometers. And here that was rounded to 2440, right? So it works. Just wanted to show you the unrounded number to verify that we don't have all these numbers as integers to begin with. So you see now you have all of these numbers rounded and still as clickable data set, right? So now I want to apply f to every row in the table. Now that's different, right? I have to go one nesting level down. I have to bump it one down because if I leave out all, then it applies to the whole table. So for example, we may ask, how many elements does every row, which equals planet, have, right? And it's 3. It's mass, radius, and the association of moons. So if we ask for the length on the second level here, that's important, right? It was bumped down to the second level after all, then we get the number of elements that there are. And it's always 3, while we know that mass, radius, and SO of moons. That's all we have here. Okay, now if you want to go one further down, apply f to every cell in the table. Okay, what length does every cell have? Well, it's 2, because keep in mind that in every cell we now have a quantity, right? These are kilometers or kilograms. But except for the moon's association, because these are not quantities, these are SOs of quantities, right? So that's what we get for mass and radius. We always get 2, that comes from the quantity. But for the moons, we get the length of the associations, right? So Mercury has no moon, Venus has none, Earth has 1, Mars has 2, and so forth, right? In a way, this is now the length of the moon association, but it is different from the first 2, because the first 2 gave us 2 because we have quantities there, and the quantity consists of 2 elements. Okay, so now let's go one level deeper. The lengths of the cells in the moon SOs, right? They are mass and radius lengths are now 0, and the lengths of the cells in the moon SOs are now 2. Those are now the quantities of the moon's masses and radii, right? These are the moon's masses and radii. What we had before was the planet's mass and radius. So now I use all, and then ask for length. And what do I get? Well, mass and radius we have already passed. They're now 0. And now we have these 2's for every one of the moons and the moon's associations, right? This is perhaps not the most interesting query, other than showing you that we now just go one level deeper, and these 2's come from the same type of quantity that we had in the mass and radius columns for the planets before, right? It's consistent behavior. We just bump it down one level by adding another all here, right? Length is now on the 4th level, right? Okay, so dataset f,n, extract the nth column and then apply f to it. So here with this, we are able to apply a function column-wise. So this basically counts the number of rows. And well, obviously this is 8 because we have 8 planets. Right? The length here gives us 8. And this is because I just picked the 3rd column here. It doesn't really matter, right? But we have 8 planets, so which column I pick, that doesn't really matter. Okay, now a sort application. Here I asked for length, and here I'm asking for sort. So sort the planets by radius. Okay, boom, right? Very simple, very code efficient. Think about this, right? All I need to do is PL of sort comma and then pick a column. And I get them sorted by radius. And you will see that we have changed really something in the order because Jupiter is now the last one. And we have Mars before Venus and Earth, right? So we really did sort. We really did sort them by the radius, and the radius is the second column. Okay, now sort the planets by mass. So here I have to sort by the first, right? Because mass is the first column. And here I have them sorted by mass. And here again we see that Mars comes before Venus and Earth. So we really did something here. Okay, extract the named column and then apply F to it. So here we're applying F to the column. And so here in this example, I do the same as above, but with named column instead of column index. So here I'm sorting by mass, right? I'm not saying sort comma 1, I'm saying sort comma mass. What if I don't know that mass is in the first column? So specify the column by name. So here they are sorted again by mass. Extract the nth row, then apply F to it, right? This is different. Here we're going by the row. So how many elements does Mars have? Well, 3. Mass, radius, and SO of moons. So we are getting 3, 3, 3 here. So it doesn't really matter, it's a 4 here, right? I just picked Mars. It could be any other one. Every planet has these 3 elements: mass, radius, and association of moons. Okay, then here we extract the named row and then we apply F to it. Right, here we have the same, but with a named row instead of an index row. So again, let's do the same query. On Mars again, here we pick Mars because it's the 4th planet. Here we pick Mars because we name it Mars, and we get the same output. Okay, so here's an interesting form. We want to selectively map F onto the nth row. Just the nth row, not everything, not the whole table, right? How many elements does Mars have? Well, it's still the same, right? It's still the same 3 that we had, but look that we're getting the entire association. But for Mars, we get something different. For Mars, we get just the number. But that's what we asked for in this syntax, right? It's selectively map F onto the nth row. Selectively map. So we are selecting Mars here by saying 4. We're picking Mars, and we want the length, and the length is 3. But we still get the whole association, and the ones that we didn't select still show us the 3. So let's click on it and we see Mars, radius, moons, right? Nothing too surprising, but we selectively picked the 4th row to give us the function application, and the function application was length. All right, here we selectively map F onto the nth column. All right, so quite similar. I'm asking for the length, and I do this in the 3rd column. The 3rd column is the moon's SO, right? So here, what this effectively means is that we are asking for the number of moons. And here we see the number of moons that every planet has. Again, full association, it was selectively mapping, so we get the full association table. But for the 3rd column, we are getting the length. And the length of the association of moons is, well, the number of moons. So that's what we get now in the 3rd column. Okay, here I've written a function application that may look a little bit more difficult, but it really isn't. We have the radii, and when we have the radii, then we can compute the volume of the sphere, right? We assume the planets are spheres, might be a good first approximation, and the volume of a sphere is 4/3 times pi times the radius cubed. So for the second, and again selectively only for the second column, which is radius, we transform this into the volume, right? So we have to say all here first, because we don't want to go over the planets. We go by columns. Here's radius, transform it with a pure function. Now, we would get an association back, and then I don't want this to show radius because we transformed it to volume. So I also need to key map over the data set structure. So I intercept them with a temp1, temp2, and temp3, because after I've done the conversion, I still have to change the label. I cannot show you the volume and then call it radius. So here I do a key map where I'm replacing the labels. And in the case of the association, right, keep in mind the third element is an association, not a data set. I have to map it over the association, right? It's an association of 3 elements. So I map it over, and this is a key map, right? I talked about key map last time. So it's not a map. We need to do a key map, but map down over the 3 elements in the association. So what we get is now these data sets. The first 2 are data sets, and here I now have volume, right? Look at the units. It's kilometer cubed, and the label changed to volume, right? Also for the second and also for the association. So see, this is also here a volume. And if you think about it, again, I'd like to call it extremely code efficient, right? If we ignore the second part here that we have to change the labels, okay? If we just focus on the computation, all we needed to do is find a pure function for the transformation and throw it right in here, right? Just throw it in our expression. And I mean, T2 and T3, I only have it 3 because I want to show you the comparison. This is really all you need, right? Very code efficient, very code efficient. You select the second column, do a transformation, and show it, right? Very, very simple and code efficient. Okay, so let's look at some more specialized forms of query. Counts gives us the counts of different values in the named column. So how many times does each radius occur? Well, only once, right? The radius column occurs only once. But we can also use a function like mean here, right? Counts is one example that was mentioned here in the help browser. But let's pick another. How about the mean radius? Now it's getting more interesting, right? This is the average radius of all the planets, 24,319 kilometers. What about the mean mass, right? Again, incredibly powerful and code efficient. This is all I need to do here. All I need to ask for in this query, and we're getting the result. 3.3 times 10 to the 26th kilograms. How about we count the number of distinct values in the named column? So how many distinct moon entries do we have? 7, okay? And this may be a bit of a leap to understand. We have 6 planets that have moons, and the other 2 have no moons. So the empty association occurs twice, but we're only counting the distinct ones, right? So let's count only the distinct ones. And let's look at this from another perspective. Remember what we looked at when we converted a column to its length. So now we're counting the unique ones, and we get 1, 2, 3, 4, 5, 6, 7, and this 0 we already had, right? So when we're looking at the distinct counts, we only get 7, because 2 planets have the same number of moons, 0. Mercury and Venus have 0 moons. All right. So we can ask for min and max, give the minimum and maximum values in the named column. Okay, so how about you show me the minimum and maximum radius? Here they are. Give min max of mass, and I get, how about we call them mass? If we want to know mass, we should call it mass and not radius, because otherwise we get radii. So here are the min-max masses. Okay, the mean, give the mean value of the named column. Mean radius, all right, I already had that. Give the total value of the named column. Okay, how about we total all the radii, right? This is now every planet's radius taken and all of them taken together. Okay. So a very interesting one comes with select. You remember I called select one of the Swiss Army knives in the mathematica system. Extract those rows that satisfy a condition. So how about we look at all the planets that have a radius less than 4,000 kilometers? Okay, so all we need to do is put in a select here. It's the first argument, and notice this is operator notation, right? And that's it, right? That's it. That's all I need to do. And that would be Mercury and Mars. They're the only ones that have radii less than 4,000 kilometers. We can look at this interactively. So let's put in a manipulate and let's change the radius a little bit. We are increasing the radius, and based on the threshold here, I'm getting an interactive data set, right? This is the threshold here, and A is the manipulatable variable, so we get a data set based on a threshold. Okay, let's count the number of rows that satisfy a condition. So what do? We use the select that we had before, but if we want to count them, all we need to do is do a right composition with length. So it's 4. Okay, so we have 4 planets that have a radius less than 7,000 kilometers. And also interactively, okay, let's change the threshold and we get the number of planets that have a radius less than the threshold. Okay, and count the number of rows that satisfy the condition. Okay, here I've got again similar examples, and I do a right composition with length and we get the 4 again, right? With 7,000 we have 4. Okay, select rows and then extract the named column from the result. Okay, that is also interesting because here we can now use a different property, right? Here we can, in the select we use the radius, but then what we want to look up is the mass. So this you would interpret as, these are the masses of the planets that have a radius less than 7,000 kilometers, right? So the selection is based on radius, the display is based on masses. You see the units here are kilograms, not kilometers. Okay, we are selecting rows, we extract the named column, and then we apply F to it. All right, so in this example, show me the total the masses of all planets that have a radius less than 7,000 kilometers. So this is similar to the one above, except that we know total them. We total these masses. So we only get these numbers, we only get one element, not a full data set here, because here we were showing these masses and here we total them. So we get one number, right? Total is a reduction operation. And again, a reminder that the data set doesn't really show us a data set if you just get one element. It just gives you that number or that string or that quantity without much fuss of a data set around that. Take largest by. Give the n rows for which the named column is largest. So planets with the largest 3 radii. Okay, all we need to do is say take largest by and put the number in the second argument, and we do it over radius. Okay, so these are the it's a full data set with 3 planets that have the largest radii: Jupiter, Saturn, and Uranus. And in the next one, we do the same one for mass. Take largest by, then comes the property, and then comes the number that we want to use for the filtering. And here we do it by mass. So here we see that it's now Jupiter, Saturn, and Neptune. I found this so interesting that I put them one by one, right? I put mass and radius in this comparison table. So you will see that the order here is reversed. Here we have Jupiter, Saturn, Neptune, Uranus, And here we have Jupiter, Saturn, Uranus, and Neptune. So the only way this is possible is because of different densities between Neptune and Uranus. Because normally more radius would mean more mass and vice versa. But that assumes the same densities. With different densities, it's a different story. So you can now have a heavier planet having a smaller radius. Right? That's exactly what we have here. Okay. So for the following section, let's get back to the portfolio data that you've already seen in a previous session. And in the following, I'll only use query. I'm dropping the dataset from now. I want to zoom in on query. So let's load the portfolio data again. As a reminder, let's look at the headers. We have symbol, the description, that's pretty much the stock name. Then comes the quantity, the price, and the security type. So let's turn it also into an association, not a data set, right? I'm only creating an association here. Okay, let's look at maximum and minimum position values. Remember, the position value is the quantity times the price times the multiplier, which depends on the type, right? It's 1/100 for a T-bond and it's 1 for a stock. So here is again how we multiply them. I had shown this in, I think, 2 sessions ago. We just take the named column, in this case quantity, times, and there's a mathematical operation here. Look at the gray multiplier sign, times price, and then times the security type dependent factor, which is 1/100 or 1. And again, what I find so very practical here is that we can use the column labels and do mathematical operations on them. This is a multiplication here, and that automatically multiplies the data, and then we can use an operation on that, a filter, a selection, or also a reduction operation, and use that in a query, right? So if we do this, then the maximum position value is in Roper Technologies, and the lowest one is in this T-bond. Remember for a moment VA4, right? Oh, this is old data. Okay, I did not, yeah, this is old data that I have used before for reasons of consistency. So forget the expiration date here. It used to be current a while ago. All right, sort them by position value. All right, now I use sort by here. This was maximal by and minimal by, and now I sort them by the same query. It's the same thing. Again, I do quantity times price times multiplier. And you will see VA4 is now the lowest position value, and at the end we find Roper is the largest position value. And dataset display can be handy. We have 46 positions, so again we can display it nicely here and scroll through it, display it, zoom in, and so forth. In what positions do I have more than 5,000? And please sort the output by price in ascending order. Okay, not too difficult. I'm doing a select again. Notice this is operator notation, and then I use a right composition for a sort by. And I want to sort by price, so this is my sort by on the right hand of the right composition. So here we are, right? More than 5,000 in the quantity. Here's a 6,000, 6,000, 8,000, and so forth. And they are sorted by price. And yeah, we see that here, 98.43 and 99 and 93. They're all the T-bills, right? There are no stocks in here. Okay, and what I also find very, very illuminating is if you peek directly at the query that the kernel uses internally. And here we see a right composition. You can always take the query and append a normal, and then you get the expression that you know for sure the kernel will be using. And when we say sort by price, it seems here the only conversion that the kernel does is that it's making it key of price, right? So when we use a string as a key, then internally the kernel makes it a key of that price, right? That's the only change here. This is a simpler one. We're gonna see more involved ones a little bit later. Show me all positions with more than 5,000 in them and display them in column order 3, 4, and last. All right, at your service. So we do this query where we ask for more than 5,000, and now I want to see columns 3, 4, and the last one, right? 3 was quantity, 4th was price, and the last one was security type. Voila, here it is, right? Very simple query, I think, right? To do the query based on a operator notation select is quite nifty. And then here is where you just specify the order, right? All right, cool. So here is a part stack query, and the kernel does a write composition with a slice function in general utilities. That's also a very, very powerful way to do these computations. We do a select pretty much like we had before, and then when I'm looking at how do you give me columns 3, 4, and last, then we see a write composition with general utility slice. We go across all the rows and takes column 3, 4, and last, right? Again, keep in mind query and then normal gives you a good idea of how the kernel interprets it internally. I didn't use any write composition here, but the kernel converted it into a write composition with general utilities backprime slice, right? And this is very fast. The slice function is incredibly fast in that it's a powerful way to rearrange the data internally. Okay, how many total shares do we have? So now we need to total them, we need to add them up. So in this case, here we first do the query and then look for quantity and then a write composition with total at the very last step. That's important. And here we put the write composition with total inside the query itself, right? Here the total is outside. Write composition total is outside of the query. And here the write composition with total is inside the query. And we get the same result. But again, peek at the internal representation to learn a little bit more about how the kernel converts these things. And the first one is pretty much the same as we had before. Write composition total comes outside of the query, right? This is the query. And in the second case, where we put the write composition total into the query, now we suddenly don't get a query anymore. We get an immediate select, and we now do a write composition on a map, and we still have write composition total at the very end. So I would like to encourage you to explore your queries a little bit. It's incredibly powerful to understand a little bit about the internal representations. Okay. So min and max quantities, please. Okay, the minimum quantity is 100. The maximum quantity is 10,000. Another case of write composition and slice, right? Take the same query here, throw normal after it, and we see that we do a slice across all the rows, filter out quantity, and as the very last one, write composition min max. All right, so this is how it works. And the query is, similar to what we had before in the dataset, very easy to modify. So in this example here, I'm simply inserting an exchange rate. I want the value of the euro.US dollar. I request it here. I call it ER, exchange rate. And here I think the dataset is better to visualize again. But I'm doing it as the last step here, right? I first want to focus on the query. So again, go across all the rows. Here I do my mathematical computation in a moment. I first want to have the first column symbol. So we just say symbol goes to hash of symbol, same with quantity. This just determines what I want to see. This just specifies which columns I want to see first. And then I want to see the price. Then I want to have a column with the exchange rate. Here it is. This is the column I just inserted, the exchange rate column. And then I want to have a column total. And total again is computed, right? It's quantity times price times the multiplier. But I want the valuation in euro.US dollar, right? So I have to divide by the exchange rate. This is quoted in US dollars, right? The settlement currency is in the denominator. So this is euro.US dollar or euro divided by US dollar. So if this is a number larger than 1, we have to multiply this. We have to divide by this number in order to get the total value in euros, not in US dollar, right? Because US dollar, the denominator, is the settlement currency. Okay, so how about a pie chart now, right? I use the query in order to specify what I want to see. I want to see the symbols and I want to see the totals again with our computed method by using multiplication on these column labels. And then I just make a pie chart and I need to use the PV, the position value, right? I store it away. I have to store it away because here then I need to use column 1 in the chart labels. And yeah, pretty easy and straightforward, right? Here you see again that row per also is the largest position value. We had that earlier. And the smallest one is one of these tables. So in summary, the query mechanism underlying dataset is query. We can use query on raw data without dataset. And a query is extremely powerful. You can use function composition in it. All right, this brings me to the second part of this session today, the web scraping of data. Oftentimes you just need to import the web location and pass the plain HTML. That is one of the easiest ways sometimes, and sometimes it's better to convert plain HTML to something else like XML. So it really depends here on the structure in which the data is returned, right? You still need to understand the structure of the returned data. There's no standard recipe for web pages unless they conform to a standard, and some websites do and some websites don't. And since version 12, we also have web execute in our arsenal, which lets you access the data directly. So you can access the elements and tags directly from the web page and process, or you can also run JavaScript code directly from your front-end session. It's one of the coolest things when you can interactively script yourself through a website, even an entire a website with JavaScript code from your local Mathematica frontend, right? It's incredibly powerful and allows you to really automate the entire exploration of a website. You could write code that lets you explore every nook and cranny of a website, unless there are logins in your way, and sometimes there are and sometimes they're not, and there are ways to handle logins with this web execute as well. Okay, but again, my warning: you still need to understand the structure of the returned data. This is usually totally inconsistent, and you have to understand what you're getting. Otherwise, there's no way you can write a parser or you can convert the data into another format. So let's start with the simplest. Let's just import some data and try to process it from there, right? Because very often what you're importing isn't even HTML, right? Not everything needs to include JavaScript or markup. HTML is the markup language, but very often we don't even need that, right? We can simply import the data. So in this case, let's look at the Wikipedia page about unemployment by country. And if we load this in, if we get this into the kernel, then we don't really have too much to do in this case, right? Because this return is so simple. Here we don't have much to do. Just look at the import to understand the data structure and then extract and parse out what you want. Oftentimes it's better to use rule replacement or XML, but here it's so simple we can just use part and we are done. So we take the first element of data, we throw away the header, and then we take columns 1 and 2 and then use a table form. I use short because it's pretty long. I'm cutting out 195 countries here. So this would be the unemployment rate by country. And we can even throw these together. It's so simple in this case, we can do it in a one-liner, right? So in this case, this is, well, what should I guess? Maybe 80, maybe 100 keystrokes, and we are done, right? We are done. But in a way, again, we're also lucky that the Wikipedia gives us this data in a sensible form, so that we just need to do import the data, right? We won't always be able to do it that way. But if we can, then it's a simple one-liner, and we have the unemployment rates for all the countries. Long list, very long list. All right. Okay, so another thing that we can do is that we pass the HTMLs and the tags, and I think I think of it as two versions. There's a JavaScript version and there's a don't need JavaScript version. So first, let's use one without JavaScript. Here we use the new web execute, but still need no JavaScript. We use web execute to get to the tags element text on the page. So some background, a METAR is a current weather observation at an airport in the United States. And a TAF is a forecast up to 36 hours. TAF stands for Terminal Aerodrome Forecast. So here we put several US airport identifiers in the URL and extract all the meters and TAFs from the returned page. And I will mention that in the United States, every Class D airport needs to have a METAR. That's a current weather observation. And some of them also have TAFs, but not all of them, right? So with Class D airports, we should expect inconsistent output. So what we need to do is that we start a Firefox session, and that comes up here. All right. So we wait a little bit until this is fully up and running. All right. And we now do a web execute on this session. And the command that we give is just we want to open the page, right? And this is the URL. And we specify the airport identifiers in this URL, right? So EWR is Newark, MMU is Morristown, JFK, LaGuardia, and so forth. A couple of airports that we have, Burlington, O'Hare, and so on, right? So as I do this, then we are sending this to the web page. And it fills, right? This browser that the Mathematica session launched for us came up, and it has the query here in the URL field, and this is the return. Okay, so we get the message that it was a success. We even get the URL back here and the additional information. The tag was open page. And now what I would like to do is parse out the tags. So I write code equals web execute, locate elements, go to tag, goes to code. And when I submit that, right? When I submit that, then I'm getting back the result, and I like to put stuff in a table form. And look that this is almost formatted the very same way. This is because the return is preserved with all formatting elements. Indentation, extra space characters, tabs, line breaks, right? That is \n and so forth. So this looks identical to the web page, right? Here is all this textual weather just as we have it on the web page. Okay, so let's look at the heads. There should all be strings, right? And these strings contain full formatting, right? They have the line breaks in them and extra spaces. So we've got everything in here, right? So let's just look at the second one, that's New York, and we have everything in it. This is a tab for New York. I'm not gonna go into it and explain you every field, but you will notice the line break here, right? This is the textual weather that pilots look at when they do their pre-flight planning. But for now, note that here's a \n, and note that here are 2 space characters. And here as well, a line break and 2 space characters. So we're preserving the formatting that we see on the web page, and the whole thing is a string. Okay? And I think that makes the display somewhat cluttered. I sometimes like to throw a panel around it, and that makes also the font a little bit smaller. So what I'm doing is that I'm mapping panel over it. I stored the whole data in result here, right? So I'm mapping panel over it, and now give me a table form. And now we see that this is formatted much nicer to read. So again, here we have a meter for New York, and here we have a TAF for New York. For Morristown, we have only a meter. You see there is no corresponding TAF entry. That's because Morristown doesn't have a TAF. They have only a meter. JFK, of course, that's big enough to give us both. So we have meter and TAF here. LaGuardia, 2. Danbury has only 1. White Plains has only 1. Teterboro has both, right? Allentown, Reading, Lancaster, North Philly, and so forth, right? We could go through this. My point is that I think now we're getting it nicely formatted. Sometimes when you think it doesn't look nice, just try throwing a panel around it. It may work, it may not work. Give it a try, right? Just try it. It preserves the formatting. It's still formatted the same way, and you get a gray box around it. If you still don't like it, try something else. But it's a good first attempt to look at this. So this is quite a lot. So how about a data set so we can scroll it? So in order to do that, I have to write a little bit of code here. That's because the Class D airports very often have a meter, but no TAF, right? So we saw White Plains, Danbury, Morristown. That's the only reason for the complication. This could be much easier if they were consistent, and every Class D airport also had a TAF. But we don't. We don't have it for everything. But if we do this, we now have a data set, and again, I kept the panel, right? I threw a panel around the data elements. And again, here for New York, we see a meter and a TAF. In a panel, formatting is preserved. Morristown, only a meter. JFK, both. LaGuardia, both. And so forth, right? We can go through it, and we can selectively scroll through it, go first one, go to last one. Here, Salt Lake City, LAX, Seattle, San Diego, and so forth. These are Class B airports, so they of course have both. Okay, so I want to say also that this table looks kind of big, right? The idea of a data set was that I can scroll inside the data set on the same screen, but now I have to scroll across screens. So I think it looks like a table that got too long. And in general, dataset formatting is a tricky issue. It has to make educated guesses based on the data types and the anticipated display outcomes. But we can get a little bit hacky. So how about we set dataset backprime $dataset target row count to 8, right? Maybe that helps us. So let's try it again. Look at this dataset. And what do we get? Voila, we get a dataset that is formatted a little bit more pleasant. It fits on one screen, and we have the same data, and we can scroll it here, right? We can scroll through it, keep scrolling all the way down to the end, and you see here we're showing 22 to 25. So here we are at the end of the table. Again, there was Salt Lake City, so we're at the end of it, and to the top of it, that's 1 to 4 of 25, right? So with this little hack, we can sometimes help ourselves out with the formatting complexities of the dataset. So, all right, let's delete the session. And a point, remember, you can always look up details with question mark, and that's a shortcut for information. Such as, well, look at everything in dataset, right? And here you see tons of them. There are so many things that you can change about the dataset. And the one that I used was the row count. Where was it here? Dataset target row count, right? Click on it and you get it. And now you see that I've set it to 8, right? Okay, so in the next one, let's go to the JavaScript-based examples. And for this example, I'd like to give you a dividend scraper from investors.com. So here we need some simple JavaScript because, well, that's what the structure of the website requires us to handle. It uses JavaScript, and if we don't script JavaScript through their web page, then we have no chance of extracting the data. So we need some simple JavaScript and a while loop to iterate over the tables. And we then append all the tables to an accumulator, and then we convert the data into XML and pass out the dividend information with an XML-based pattern matcher inside the cases. Sounds complicated, but it really isn't. So let's start a new Firefox session. It came up, it came here. Again, it just brings up the session and there's nothing in it yet. All right. So, and in the next command, we just want to open it, right? And we get it here. The last trading day before I prepared this notebook was June 14. I prepared this notebook on Sunday. So the last trading day before that was June 14. So that's why I had June 14 here in it, right? So we execute that web execute, and here's a little bit of code, some smart code that extracts the data with a JavaScript execute. All we need to do is provide some smart JavaScript here in the JavaScript execute tag for web execute. So this is basically an accumulator. We start with an empty list and we do a while loop until the head of string is no longer failure. That's when we iterate through the loop, and we always read it and we're accumulating string into the string list. That's what append to does. Remember, append to and prepend to change the underlying structure. I talked about this in a key context with associations in the last session. So append to actually changes string list. So this is a handy way to accumulate. So, all right, this has already executed. You see that everything in here is without any blue remaining. And now let's map an import string where we convert the data into XML. And at the same time, then we also want to take this div list. And here we do a pattern matcher, right? You see that we are converting an XML element into just the data that we want, right? We want A, which is the company name, and the dividend, which is two expression of B, right? Because it comes back as a string. So you need to understand the data, look at it, understand the structure, and then I think you will be able to understand that we have an XML element here of this form. I believe I've done it most efficiently in this rule replacement. There's many things you can do right or wrong here, and you can also do it efficiently and inefficiently, right? That's not wrong, right? But there's efficient and inefficient. I believe I found the minimal representation here, and then you just display it as in a table form. So let's compare to the web page output. So we have American Tower rates at 1.82, that's here, and so forth. We go down all the way to Winnebago Industries at 11 cents, and that's all we have here. So quite successful. So what did we do, right? We opened the session, we opened the page with a specific date in the URL. We needed to do a little bit of an accumulator in this parsing of the blocks that we extracted with the JavaScript. Then we converted this into XML, and then we did an XML parser and have the data in a 2-column table. Okay, in the next example, let's look at stock options on Yahoo Finance. And that is similar as above. We use some simple JavaScript and a while loop to iterate over all tables found with the JavaScript snippet. We accumulate the tables, we then convert to XML, and then make separate extractions for the calls and puts with an XML-based pattern matcher inside cases. Again, not too difficult. May sound difficult, but it isn't. So let's open this web page here. These are the options on Microsoft, and we just open this Yahoo page here. Again, we run our accumulator code where we are just iterating through the blocks that we generated with the JavaScript execute. With the accumulation is now in string list. Make sure you always set it to 0, otherwise you're appending to the chunk that you've created before. And now I map import string into XML over the string list, and I now want to have it into a call table and a put table, right? So that is important because I really want to display them separately. So I take options list of 1 for the calls, and I take options list of 2 for the puts. So if I run them, then I get a call table. And let's compare to the web page, right? So the first one, let's just look at some of these numbers and check them out. I can't do that because of the ads. All right, okay, so, all right, then let's focus. This is 560.94, and we have 560.94. And the last one is 57.81. 57.81, right? So seems to be correct, and we do the same with the put table. I mean, Microsoft has a lot of options. I picked a really big example here, but fewer puts, right? Look, you will see that the call list is a bit larger than the put list here, it seems. So here we have 262.50%, 262.50%, and we're ending with 68.95, and we have 68.95. All right, so it seems that this options parser is working. Okay, so for the next example, let's scrape data from a web mathematica page. The return of a JSP page is usually plain HTML. That's how most people are writing their JSPs. They don't have to do it that way, but that's how it's usually done. So we use web execute and a simple JavaScript snippet to find tags that tell us type element and click element tags. We need those to fill the input fields and then click the submit button. The rest is like above. The iterates over the tables, the accumulator, except we now have HTML and not XML, right? And I specifically want to treat it here in one example as HTML. It's a bit more complicated, but I want to make the point that with the string manipulation functions in the kernel, you can still get very powerful results, and you may not always be able to convert everything into XML. So that's not a problem. HTML is easy to parse, and we convert the HTML to XML and parse out from that as well. So the first one is going to be just HTML, and the next two then will be XML. So I have a Web Mathematica license, and you will find that here. So let's open the Web Mathematica page that I have on my Web Mathematica server. It's a credit card pay schedule using only minimum payments. So in 2010, the Obama administration changed some credit card laws. It's now required that credit card companies charge at least a minimum payment amount every pay period to make sure that the outstanding amounts plus interest plus accumulated interest cannot get so big that people can no longer repay their credit card loans. So there is now since 2010, there's a minimum payment amount and you have to pay at least that amount. You cannot defer the repayment until indefinitely. So if we look at this one with these default input numbers, then we get a comparison table and a payment schedule, right? So in the comparison table, you get something like minimum monthly payments, months to repay, total interest, and the interest as percent of principal. And then comes a payment schedule. And when it gets below the minimum payment amount, then you have to pay that minimum payment amount to get it really down to zero, right? So the method switches from the payment amount that you have without consideration of the minimum payment amount to the minimum payment amount, and that's here at this point. From here on, it's always $15, and we always subtract now those $15 until we're really down to zero, right? Until everything is out. All right, so that's the idea, and this is a computer to figuring out these numbers based on these inputs. And let's do it programmatically from the Mathematica frontend. Again, I get a new session, right? When I do a new web session, I have a new one here. And now let's web execute it, and it immediately put this into this page, right? This is the web execute that just came from the previous statement, the start web session. All right, so now you see my web Mathematica page in this browser that the Mathematica session started. And now perhaps I should keep this on top of everything. And now I want to define again my tags as my inputs. So I define this, and now I am literally scripting the input fields on this. So look at this. This was 1000, 0.18, 0.03, and 15. And now I'm sending this into my browser, and we suddenly have 2000, 0.163, 0.03, and 15. Right? The next one here, I need to click. Right? Okay, so I could hit submit here, but again, we want to do it programmatically. So I execute this line here, and it does the submit, and the submit immediately computes everything. So here you see everything with the numbers that I have provided from my Mathematica session, right? That's the difference, that's the kicker. And let's accumulate. Let's look at a couple of things. We have 6 blocks in the return. I think we discard the first 3 because of the structure of web Mathematica. You always clear out at the end of the page and start at the beginning. So our first of interest should be 4. So, and my point here is you can pass it out any way you want. And I chose CSV for this example, no XML intentionally, even though XML is easier. So I can show you passing with string cases. And this needs a little bit more cleaning up than if you use XML with replacement rules. But you see that the pattern matcher string in string replace is short and similar to a rule-based pattern matcher anyway, right? So let's look at this. If we import this as a CSV, this is the first table, right? 4 is now the first table from the return. And here is what we have from the HTML return, right? You see this is typical HTML blah blah, and as a CSV. And now if we craft a clever parsing string here, right? Anything at least 2 elements, then comes name, and so forth. We're extracting it and convert it into just a list of 2 elements. And then we are pretty much done immediately, but we needed a pretty clever string for that. So we have basically our inputs back, right? Here we have the 2000, the 0.163, the 0.03 for minimum payment amount, and the 15 for minimum. Okay, so this may look like a hassle, but keep in mind, when you're designing your replacement rules for XML elements, it's not easier, right? You may prefer the replacement rules, or you may prefer string cases, right? This here is not more difficult than the replacement rules that use XML element. Okay. Incidentally, as this code for specific data segment, we wouldn't have needed to pass it out with the row labels. We could have pre-hard-coded them, as we know ahead of time they would never change. Well, yeah, it's not a surprise, right? It's principal, APR, minimum payment percentage, and minimum payment amount. So strictly speaking, I can even say that this passing string in the string cases is too complicated, right? We know name and we know value. Right? So we could even have done it easier. However, usually XML is easier. XML conversion and then a pattern matcher, it's usually much easier. So for the comparison table, and for your memory, that was the comparison table. Okay, so it's good. We import now block number 5 as XML, and I call it XML. And I now parse out the XML element, and I think I found a very efficient matcher here. I don't think you can do this any shorter. And all I want to know is, well, the number, right? So partition it. And when I do this, then I get this output here and compare that to the table that we have here, right? It seems to be matching. Yeah, it does. Every number matches here for the comparison table. Okay, that was string list 5. And for the payment schedule, okay, so this is going to be a little bit longer. This is now a string list element 6, that is block 6. And in this case, I don't remember, the same or similar pattern matcher. Give me the element. This really just means return me the element. Infinite nesting level. And here we have 3 columns. I find it easier to reformat this with a partition comma 3. Right above here we had a partition comma 4 because we had 4 columns, and give me a table form. So this is now the repayment table, and here as well it seems to be matching, right? So everything we have in here seems to be the same as in here. Let's compare first line and last line. Yep, they seem to be matching. Okay, but for very large data tables that we want to analyze, well, we know that we like Dataset, right? Because it's an interactive table. So let's pass out the first element, because that is going to be the column headers, and the rest of the schedule, right? Rest is except for the first line, everything except for the first. So they're frequently used together, first and rest. This takes the first and this drops the first. So taking the first is the header and taking everything else is the data. So let's take it and take it in a data set. And here we see 129 columns. Okay, that's because I set the row to 8, right? That's what I did. So if we look at this again further up, I don't know if I find it quickly now. think it started with dollar uppercase data. What was it? Row target count. Here we are. So let's take this row again, go to the bottom of the page. So let's go back to 12. I think it was 12 or 15 as the default, and get a bigger list. Okay, how about 24? What do we get? Okay, it's a bit much for one page. Let's try 20. And there is a nice data set with all the lines, 129 lines, with proper column labels. And you will see that it's not just a line of strings, it's with an underlying background. It's clickable, so it's a proper data set, and we can fully interactively go through it. Here's our last line that we had before. I think we have a good data set done with web scraping of free data on the web. All right, this brings me to the end of my session, and I hope you had fun as much as I had, and I will see you next time. Bye-bye.
Okay, thanks, Andreas. Let's see, since there is no question on our Twitch channel, I think it's a good point to wrap up our today's session. You are watching the 5th live coding session with Andreas Lauschke. You can find a playlist of Andreas recorded videos on Wolfram Research YouTube channel. You can also interact with Andreas directly through Wolfram Community website. Thanks for watching and have a good one.